We're resuming the atmospheric circulation lecture. They're pretty long lectures, so I wanted to take a break there and give yourself a minute to orient. So let's just do a quick refresh. Okay. We went over the density of air. We talked about warm air rising and cold air falling based on density. We went over the pressure of air. Warm air is low pressure. Cold air is high pressure. Warm air rises and cold air falls because of it. We then talked about uneven solar heating. The sun's rays have a more direct and smaller space to hit on the Earth, and an indirect and larger space. The coverage is larger in the polar areas. So again, consistently warm in the center, consistently colder at the tops and bottoms. And the figure that we left off on, because of that, if we had, and again, this is the key part, if we had a non-spinning Earth, we would literally have cold air falling on the equator because it would be so heavy it would push it down. And then that warm air would attempt to rise up in the tropics to then warm the poles. Now, I had mentioned a fancy name, the Coriolis effect, and that has to be the next part of our story, because remember, we're spinning. We're spinning on an axis that's actually tilted 11 degrees to the east. Okay, so we're more like this as we spin, as opposed to straight up and down like this figure shows you. Think of if you play with a globe, right? You never spin that globe literally horizontally all the way around. Instead, you spin it on an angle. So if we apply that angular spin, we're going to be applying something called the Coriolis effect. I'm going to give you a cartoon to take a look at first. That cartoon is found, of course, the larger PowerPoint. That cartoon is a Calvin and Hobbes cartoon, and it's probably the way that you're feeling right now. It essentially says that this is such a large concept to grasp that it's a little overwhelming, right? Calvin gets a little overwhelmed. But it's really not that bad, okay? Because if you think about what we've already taught you, that of course the Earth is wider in the center, which is again why you have direct solar heating, and it's angular or skinnier at the top and the bottom, then clearly when this globe spins, think of a basketball on a finger when it spins. If this space is shorter in distance than this space, then if you were a spot on the ball to spin all the way around a circle, right, to go literally all the way around, that path is a lot longer than if you were a spot on a circle and you had to go all the way around. So the track path that you would cover in an equatorial region is larger because it's fatter, and the track path that you would follow in a polar region or temperate region is smaller because it's skinnier. Now remember, we're going to take this and we're going to tilt it. So what you're actually going to do is apply the Coriolis effect. Just to give you a quick definition of the Coriolis, I don't usually give text slides when I'm lecturing this way, but again, just to make sure you understand what it means. It's the deflection or the apparent deflection of objects moving across the Earth's surface to the right of the direction of travel in the northern hemisphere and to the left in the southern hemisphere. This is because the differences of speed and, of course, the width, the distance they have to travel at the equator versus the poles. Why would the speed be different? Cold air is heavier. Certainly it travels at a different speed than warm air. The width itself is easy. If the track is smaller or bigger, then clearly you have a greater distance to cover. At the equator, though, where you have the greater distance to cover, you have a faster speed. At the poles, you have less of a distance to cover, but a slower speed. So it's going to increase poleward as speed increases. Coriolis deflection, of course, is going to increase poleward as speed increases. Here's a figure. This is called a roundup, one of those typical toys that you play with at a playground. You always like to situate yourself in the center because then you get less dizzy and you feel the centrifugal force not as bad. Or they have those crazy gravitron machines in amusement parks where they make you sit in those cages all the way around the edges, right? If you have those edges all the way around, half the time you can lift your head up and the other half of the time you can't, right? That's because of the force that's being exerted on you as you spin on that path. Well, what this is representing is if you were to throw an object, this is you, if you were to throw an object along a straight line and you weren't moving, you could throw it and the person could be directly across from you and you would catch the object. But what if you're in that same location, but you're on something that's moving, whether it be to the right or to the left, to the clockwise or counterclockwise path? That path of the object is actually going to veer in direction to the right in the northern hemisphere and to the left in the southern hemisphere. That is the Coriolis effect. So again, it's showing us that we have a rotation of the Earth. We are spinning on an axis. We're spinning to the east, so everything is moving from the east to the west from a wind pattern. And that means that the deflection is going to be to the right in the northern hemisphere, making it look like a clockwise spiral, and to the left in the southern hemisphere, making it look like a counterclockwise spiral. So we've now added the Coriolis effect as another component of our atmospheric circulation. Right? So again, what they're showing you is if you were to throw a ball from the northern hemisphere and throw it downward, the path is not a straight line. If you're standing here and throwing it northward, the path is not a straight line. You veer to the right or to the left when viewed from above. And that's how the Coriolis effect applied. When you do this portion of the lab in Lab 6, we videoed a series of essentially spinning discs and showed you what these figures will look like because you guys are not able to do it yourself in the lab. But I want you to remember that when you're viewing the spinning discs, you're viewing them from above. And so that's always meant to represent you're viewing it, from the northern hemisphere, from the North Pole, from above looking down. So you're going to end up again with a clockwise pattern in the northern hemisphere, again, because the turn is to the right. It's a right-hand turn. And a counterclockwise path in the southern hemisphere because it looks like, even though you're coming from the same direction, it looks like you're veering. Okay, so quick summary. We've now brought ourselves full circle back to the wind patterns. And we now know that there are a series of impacts as to why these wind patterns are. We have pressure, low in warm areas, high in cold areas. We have uneven solar heating, smaller and direct at the equator, further and indirect, more coverage at the poles. We have wind patterns originating from the east because we're spinning toward the east. So if they originate from the east, we begin with easterly winds, then we bring back westerly winds, and then we bring back the easterly winds, which gives us our three wind patterns: east, west, and east. And of course, we have our temperature changes with warms and colds, colds being more dense and warms being less dense, so they travel in different paths. What I want you to realize now is that we're going to do the second half of this lecture, which is the ocean circulation lecture. What we're going to do is literally apply the wind patterns that you've just learned, and we're going to apply those winds to blow over the water. Okay. You want to remember, we've seen this figure multiple times, we have three temperature-based patterns: tropical, temperate, and polar. So we have cold water and air, warm water and air, and middle or temperate water and air. That's the same as your 0, 30, 60, 90. 0, 30, 60, 90. Remember, we have spinning to the east Earth, so we originate at the doldrums with our easterly winds. East, west, east, from the east or from the west. So let's clear this image up. If we were to blow that wind with all the factors that we just talked about over the water, and we add our last component of the Coriolis, what must happen? We must have a deflection to the right in the northern hemisphere and a deflection to the left in the southern hemisphere when viewed from above. That means that you have a clockwise spiral or gyre in the northern hemisphere and a clockwise spiral or gyre in the southern hemisphere. And this is where we'll pick up in the next lecture with the ocean circulation.